All right. Hopefully everyone can hear me and see my screen. Today we're going through the workshop on high performance computing and open ISAs, focusing on RISC-V and OpenPOWER. We have a full packed day for everyone. Excited to have you here. There's a bunch of interesting talks and a sample of what's available here, both from research and academia. So let's get started and go from there. As I mentioned today, we have basically 4 different sessions. We have 30-minute talks in each session by a variety of different speakers from around the world, which is exciting. We're going to be looking at a variety of different topics and processes around open ISAs, both RISC-V and OpenPOWER, as I mentioned. They're broken up into sessions. Each session has a series of 3 to 4 talks, 30 minutes each, 25 minutes for the talk, and about 5 minutes for questions and answer. In between the sessions, there are several coffee breaks or breaks, lunch breaks, those types of things. And we've set up a bunch of Zoom rooms we will post in the chat to everyone. The links to that for each of the speakers if you want to continue the conversation. So if the speaker is available in these 30-minute either coffee breaks, lunch breaks, or what have you, and even after the wrap up, they'll be available to talk and go through all the process of continuing the fantastic conversation about their work they're doing and all those good things. So very excited to have everyone here. Thank you for joining us. And we'll go through some of the logistics before getting into any of the details on the talks. So it's pretty straightforward. The webinars themselves will open up 15 minutes before their start times. All sessions are recorded. Our hope is to put the recordings online and available for you and others to see, as well as the talks themselves. So we'll put the slides up on the same page and link those to the talks that the speakers provide as soon as they're provided. So we kindly ask you to mute your audio. If you're a panelist, you have the capability to use audio and video. All the other participants do not, as set up by Zoom. Hopefully that makes sense. For the Q&A, if you look at the bottom of your screen, there's a little Q&A icon that I'm highlighting here. If you have a question during the talk, please type it into the Q&A window, and the session chairs will go through and read them to you or to the speakers so that they can answer them. Likewise, at the end of the session, as I mentioned, we'll be posting in the chat for everybody the links for the various speakers. And you can go through and connect to them and have conversations with them or others on that particular topic. So it should be pretty straightforward and easy from that perspective. And hopefully you're familiar with Zoom, that you've seen this before. So it should be pretty straightforward. All right. With that, let's get started. So today is a very interesting, exciting day because what we've been talking about at the BSC for the last over a year or so is a transformation in research and technology where we see that the future is wide open. And what we mean by that is a stack which is both open source software as well as open source hardware. And so that's the exciting part of kind of looking at what's going to happen in the future. Now, what is the reality? As many of you know, the reality is really the upper part of the stack today is open. So this is the software components. And this has been led by proliferation of Linux and open source software packages and components all on top of that. And that's throughout the whole space. And this is across a variety of different places. So from small embedded systems, IoT, all the way up to cloud and even high performance computing, all have components of open source software, and that's being used by a bunch of people. Community supports that. And that's pretty exciting because you have a common platform, you have an easy way to contribute and see what's going on with the code. There's nice security options in terms of being able to have that visibility. And really, you can have a large crowd help with the development and support of these things. In the end, generally a company will probably be necessary to support the overall ecosystem for a particular slice or application or development, but that's kind of where we are today. Now, the other interesting aspect is we're starting to see some of this move into hardware. You could look about 10 years ago with the Open Compute platform, where the hardware infrastructure for hyperscale data centers was being pushed in the open. You could also say that some of the standards that are available are also in this space. But when you got into the CPUs, GPUs, ASICs, that basically was closed source. And the things that you buy today, whether it's from Intel, IBM, AMD, pick your favorite hardware vendor for processors, GPUs, NVIDIA, those tend to be closed. And so the challenge that you have is if you're looking at the system as a whole and you want to be able to optimize it, really that block or barrier at the hardware level inhibits your capability to do some types of research or makes it much, much harder to do in that context. So architecture has basically been simulation. So what do we see today in the technology trends? And that's the interesting aspect. So as I mentioned before, we have this massive penetration into the software stack from IoT all the way to HPC. Again, various systems being built around that, Linux being kind of de facto standard for operating systems in general. We have this other interesting aspect of Moore's law diminishing and ending. That ability to give me double the transistors every 18 months to increase performance really prevented a focus on a lot of ASIC development just because you could wait 2 years and a general purpose processor from your favorite vendor would do more. And so this combination of the lack of Moore's law and power constraints have really pushed us into a new regime of specialization. We need something that's more cost effective, more performant, lower power, all to fit within that envelope. And HPC and other areas are really pushing that space. So really now we're getting to this regime where software as well as hardware combined, that co-design is the way to achieve those performance characteristics. And so this new open space for hardware to come in, and obviously it's a great time to be around because we have the proliferation of things like RISC-V and OpenPOWER. These are by no means the first, but it seems like the time is right in terms of a combination of technology, requirements, software, and the success we've seen in open source software. How does that translate into the open source hardware space with these open ISAs? So a lot of that's going to be discussed today. We'll see many different projects across the world where they're really looking at how to do that. But I think this is the right time and the right place. So let's start with a brief history of Linux just to highlight some of the kind of timeline to see where we are today. Obviously started development in the early 90s, based in Europe. A bunch of interesting components came out, but about 10 years in, we saw an adoption of a variety of different major companies supporting or trying to figure out, I think more so, what to do with Linux and how that works. And so that was an interesting kind of inflection point in the marketplace of what to do. Likewise, on the high performance computing scale side of things, Mare Nostrum was one of the first supercomputing centers to deploy Linux as its de facto operating system. And so this was a big change from vendor-specific operating systems from previous supercomputing deployments. So pushing the envelope and getting this in place, and today that's basically the norm. And so now, you know, the amazing thing about today is we see Linux just dominating a lot of the different environments in various forms and flavors. And so this is just something to kind of keep in mind when we think about how will the hardware space evolve, how will that move forward. So what we're seeing on the RISC-V side, obviously a very abbreviated history there, started in about 2010 at Berkeley, and the foundation was later formed in 2015. And by 2019, there's over 1 billion CPUs have already been shipped. And so that's a massive uptake in that. And so we see this interesting confluence of events giving us rise to the ability to not only use this open ISA and OpenPOWER and others are like that, but also drive interesting research and development across the board. So again, have the same type of span, about 10 years, and major companies were adopting them. So it's exciting to relive history, but on the hardware side. And then furthermore, see how quickly this will accelerate based on just the time and age of the internet. So when we combine all these things together, what we get is this fantastic capability to move into the CPU, GPU, ASIC space with these open ISAs and do it in a kind of crowdsourced way. And so really we have this capability to create these new ecosystems on the software and the hardware side with this. And so that whole world now becomes open. We can provide these open source ISAs as alternatives in research and in industry to look at various solutions that are non-EU, right? So the US, China, Japan are dominating at least the CPU and accelerator space. And so now we have a capability to do something new, and that's exciting. And so really what this gives us the opportunity is to provide technology independence across the world. So EU, Africa, Asia, there's all these different places that we can use this in a variety of different ways. And we're seeing a lot of interest there. And so this is where we are in the sense of early adoption in that cycle in around 10 years. And so Linux plus this combination create this full stack from whatever your hardware widget is all the way up to the applications. And the key there is how do we build up that ecosystem and leverage both open source software and hardware to kind of rebuild this new industry where we can customize and from a research perspective, drive innovation from that perspective in the co-design space. So I think that's very exciting, and that's kind of a future that we see moving forward. So just to give you some background in what BSC is doing, and you're going to see a bunch of talks in these general areas, is what we're doing in the context of RISC-V and open ISAs in general, and how we're embracing that broadly. And I'm going to go over a couple of different things today just to give you background. So one of the major initiatives is LOCA. It's the European Laboratory for Open Computer Architecture, looking at full stack design, so software to hardware, building out chips, bringing that capability to build systems based on both software and hardware, emulation, all those things into the fold so that we can really drive innovation, research, and technology there. And by putting this under that umbrella, we can then create research artifacts that are higher quality, given that our goal is to produce chips, research chips, that then can be handed off to industry to take forward. There are many projects that are going on at BSC and other places that are driving this. One of the first around a large-scale RISC-V deployment was part of Horizon 2020 and EPI, the European Processor Initiative, in the first phase. I'll talk to, and there'll be talks about that today by others. I'm going to go over briefly what MEEP is. It's the Mare Nostrum Experimental Exascale Platform, how we're building that out, what its goals are, and there's many other kind of Euro HPC style research projects there. We have other ones at BSC and others that some colleagues of mine will be talking about as well, giving you insight into what we're building. And of course, there's a very interesting kind of groundswell on how do we have a coordinated effort, how do we work together to build that ecosystem, both in Euro HPC or the HPC space as well, but also working with highly relevant adjacent ones in Europe. So there's the microelectronics, DG Connect, DGIT, all of these different kind of streams of research and research funding give us capabilities to build this out. And of course, there's the entire industry around that. So again, I think to create a successful self-sustaining ecosystem, not only research has to be involved, but it has to be handed off to companies that then can commercialize and obviously give back and make money from that process. So exciting things today and moving forward in general. Now, obviously, we're not the only ones thinking about this. There was a conference in Brussels in November of last year, which was really looking at open source, not only from the software perspective, but picking up on this hardware theme. And so some of the big issues was, how does Europe support that? I'm sure that's happening worldwide, but this is just an understanding that there's other groups, other research areas outside of high performance computing that's looking at that. So that's exciting to see this momentum in that direction. Now let's change gears a little bit and talk about LOCA, so you can kind of get an idea of what this umbrella organization is doing. I think it's a very interesting thing to think about. How do we work together and think broadly of the infrastructure necessary to support open source hardware and drive that in the same direction as software. So for those that don't know about BSC, just at a high level, there's 5 different departments. You can think of 4 of them as kind of application areas: computer science, life science, earth science. There's applied engineering case, and then there's the actual operations. So we have this whole layer of application software work and all the components in that, all the way down to architecture as well. And then we have a deployment as a supercomputer itself. So the picture behind me is Mare Nostrum 4. I'm showing it in the slide as well. So there's an opportunity to look at these application domains, do the software hardware co-design, build that hardware, and then deploy it in the supercomputing center. And so this is really a first step of what we're doing with MEEP, and I'll get into that later. But this is this exciting space where we can look at all facets of the hardware and software and then co-design appropriately for the application domains. So very exciting from that perspective. So the goals of LOCA are pretty straightforward. Really, we want to look at this as a mechanism or facility to extend open source ecosystem and hardware, looking at bringing expertise into Barcelona and Europe in general. So it's really a wide range of opportunities, and really leverage the existing excellence we have on the software side to then extend into the hardware and build these chips on a regular cadence, focus on high performance computing and other related topics or adjacent areas. This means that we need to bring up part of the infrastructure, which is, well, how do we deal with IP? What's the open source repository? Those types of things. But in the end, we want to put out proven hardware software stacks that then can be demonstrated in reality. And so from a European perspective, this will be a great catalyst for European IT community and drive that whole process moving forward and reimagine research and industry collaborating in a very interesting kind of incubator-like manner. So again, fantastic from that perspective. Now, how do we do this? And that's the harder question, I think, to answer. And so when we step back and we look at traditional chip design, what we've seen is there is a master apprentice environment that's an industry that exists. And so you have chief architects and senior folks that have built chips and systems working with younger people that come out of school in various degrees to come together to make an amazing piece of hardware that then software runs on top of that. And so what we want to do is basically create an environment where we can bring these masters and apprentice kind of folks together from academia and industry, work on these projects that are targeting different types of innovation in hardware and software, and create this kind of collaborative sandbox where you can work on these interesting ideas and then have an artifact that comes out of that. And so really the whole end goal is to look at various major thrusts or design areas, drive those to a completion, and build that in an academic environment. So I think from an industrial standpoint, you get to do things that are more risky, more innovative. And from an academic perspective, you get the reality of, well, how do we actually build these things? What do we do? What makes sense? And that kind of thing. So that combination will give us a very exciting piece of information and capabilities moving forward. So I'm excited to continue to build this up. And if you're interested, please don't hesitate to reach out and we can talk about it more. Now, the interesting aspect here is when we think about Barcelona, they have these Castellers, these human towers. And this is a great metaphor for open source and part of the motivation or inspiration for the logo. And so you have a large base of people at the bottom, like the open source community supporting this. And then you have many, many tiers of this. And at the top here, there's a little child that actually goes all the way up. but this person couldn't do this without all the people below that. So we can build on top of the shoulders of giants many great things. And so that's really what we're thinking about as we leverage open source, build out these communities. And you'll see in some of these talks that they're using components from various places. So that's pretty exciting. All right, so switching gears right quick. One of the first aspects of LOCA and building this out is MEEP, the Mare Nostrum Experimental Exascale Platform. And this is a co-design laboratory. So we're building out infrastructure for software and hardware development. And the whole goal there is create a sandbox where we can test out ideas and go from there. This is associated with the next Mare Nostrum 5 procurement. So we have a 200 petaflop machine and this research vehicle next to it, which is pretty exciting. So at the high level, the big question we're trying to answer is, for an HPCL style accelerator, that's exascale, targeting 2025, what would you build? And so we can use these field programmable gate arrays to build up an emulation platform. And it's an abstract emulation platform, so it's not gate-to-gate true, but we can use this to do validation of performance and pre-silicon IP. We can look at this from a software development vehicle, put all this together, and then test out these ideas at scale. So think, say 100 or so FPGAs at that level, working with host processors. Now, the nice thing about this is we believe that the things we're building will be flexible and reusable. And so we can use it to enable other software or hardware projects at BSC or in the EU. So when we look at all these other projects, it's a base stepping stone to get there, both from the physical platform level, the emulation IP, so the things that make the FPGAs work as we expect them to do from a base level, and then bringing in the software and the hardware IP, and ideally making it as much of that open as possible. So there's a couple of different pieces, and this is basically in a nutshell. We have a software ecosystem, and we're looking at all the software layers from the operating system up to applications, including both traditional high-performance computing as well as data analytic applications. Mapping that onto the FPGA system, where we have some type of host server with 8 FPGAs connected to them, leveraging the OAM, the Open Compute Accelerator Module form factor, and commodity off-the-shelf components. Pretty cool to be able to do that. From the architecture perspective, it's pretty straightforward, looking at both dense and sparse compute platforms. In that context, the dense side really tells me how many floating FMAs I have. On the sparse side, I'm really looking at the memory system and how that works. Targeting chiplets and HBM in the future, and that's what we see kind of driving technology, both from a scale perspective, integration perspective, and yield. We're at a high performance computing center, so looking at things like vector lanes, systolic arrays, those types of things. And there'll be a talk later on architectural simulation models that we're building to enable these larger scale simulation components. So look forward to hearing about that. On the software side, it's everything from traditional HPC and high performance data analytics, so LinPack, HPCG, GROMACS, those types of applications, and then moving into AI, machine learning, and deep learning, looking at the various runtimes, OpenMP, Comps, Apache Spark, TensorFlow, and the components around that, whether it's Kubernetes or something else, Docker as containers or Singularity, Linux, and then playing with the programming models as well. So the programming models can be a traditional offload model like we see with GPUs, or moving into a self-hosted space. And of course, there's all the other infrastructure around that, the compilers, profiling, tuning, debuggers, all those things to make RISC-V more amenable in that context. Now, on the FPGA side of things, how do we build out the FPGA shell? So this is the baseline infrastructure that I'm showing also down here. So PCI Express, Ethernet controller, some FPGA to FPGA links, the HBM controller, really building on top of what's available from the IP vendors in that space, but also then having a canonical interface, this kind of blue layer here, which then gives us a standardized interface to the emulated accelerator or whatever else we want to put in there. So again, looking at all those different pieces to make that work well. Now, there's not only the hardware side, but there's also the software side. So PCI drivers, making Linux work in the environment that we want to work in, looking at the RISC-V software stack in general and how we move that in, and then obviously bringing in the tool chain and those components as well. So that's, I think, pretty exciting from that perspective. with that, basically, you can see that how we're going to combine the software and the hardware, map that onto the FPGA, and then come up with a series of open source IPs, being able to rapidly prototype these systems, and then do the software hardware co-design and validate that. And of course, really, in this project focused on RISC-V and how do we make that a better ecosystem across a variety of different software and hardware components. With that, I am going to pause. We have time for a few questions if there are any. And so if you'd like to ask a question, please go to the little Q&A spot and I'll read them out and we can kind of go from there. So we have a first question from Jose. What is the size of the FPGA prototype for emulation? So the FPGA that we're targeting is a relatively large FPGA, probably about 3 million gate equivalents. The platform that we're looking at is using 8 of these FPGAs connected on what Open Compute calls a universal baseboard. It has full connectivity between the FPGAs. Within the FPGAs, they have you know, the normal types of things, DSPs, block RAMs, that kind of stuff. They also have connectivity to HBM and have an HBM stack. And so we have a very nice number of capability there. So the overall, let me just go back one slide to get to this picture. So the overall context of this is a node, right? So we have a dual socket server, most likely x86, connected to 8 FPGAs and having 10 of those systems in 2 racks, giving us about 80 nodes to play with. We would map emulators onto each one of the FPGAs and go from there. All right. So there's a question from Abhishek. Since RISC-V is a free ISA, but the ASIC CPUs built are licensed by the company. So I don't understand how RISC-V OpenPOWER will make it open. So if you look at what's available today on the RISC-V side, there are several companies that are producing processors which are closed source, and there's several academic and others, in some cases, companies providing open source versions. So you can download the RTL, Chisel, BlueSpec, System Verilog, what have you, and then build the system from there. If we're mapping it to an FPGA, it's just going through the process of synthesis, place, and route. If you're doing it for an ASIC, then obviously there's a whole physical design backend that you have to do. So from that perspective, you have capabilities to map to that level. Hopefully that answers that question. All right, so we're coming to the top of the hour. What I'm going to do is, so session 1 is coming up. I'm very excited to have a variety of different people talking about their work there. Hopefully we can continue this conversation offline and talk about this, but you'll look at a variety of different things. First up is Dan. He's coming to us from Washington, University of Washington. He's a PhD student at the Paul G. Allen School of Computer Science and Engineering. He leads the development of a BlackParrot project, which he's going to talk about today. His research interests focus on engineering hardware, designing flexible microarchitectures, and agile test chip tapeouts. He received his BS and Masters from UIUC, where he looked at wafer scale systems. And with that, I am going to stop sharing and hand it over to Dan to take the reins. All right, Dan.
All right. Hopefully this works. Okay, great. Yeah, thanks for the introduction. My name is Dan. I'm a student, PhD student at the University of Washington. And today I'm going to introduce BlackParrot, which is a RISC-V multicore that we've developed at the University of Washington in collaboration with Boston University. So traditional hardware design methodologies rely on this expensive tooling and proprietary IP libraries, as we just talked about. Only recently are open source CAD tools approaching parity with these commercial offerings. And this is really exciting because it allows researchers and hobbyists to get involved in the ecosystem of taping out chips. Because these open source offerings reach a wider audience than the traditional methods, there's more of an increased demand for libraries which provide new users with basic building blocks, as well as veterans with flexible verified components. It's no coincidence that this is happening when we're in an era where diverse workloads demand custom silicon. With the end of Blanchard scaling, accelerators are exploding. And we need to be able to continue to provide performance and energy gains without traditional scaling effects. While custom accelerators are the secret sauce for these new systems, they don't really stand alone. Developers of novel accelerators need to maintain uncore, I/O, chip-specific components, and debug interfaces to test their chip. And getting any of these components wrong can ultimately take away from all your hard-earned acceleration gains. So general purpose host cores are needed in order to control these accelerators and coordinate cooperation between the various system components. The way this is done traditionally in prototyping is to have, as we talked about before, like an x86 processor that actually controls the system. Let's see why this keeps on going ahead. Okay. So an ideal host processor needs to meet the system performance, power, and area requirements, else we can't use it. It needs to be able to control a diverse set of accelerator types, connecting easily to both standard and custom interfaces, and using standard languages and design methodologies. It needs to be trustable. If the IP needs extensive re-verification or redesign, we've lost the benefits of reuse in the first place. And it needs to be free and open source. We need to be able to experiment with the design without purchasing a license and be able to freely modify it so that we can just simply attach our accelerator to the host system for rapid, realistic prototyping. If developers can bring their own accelerator and immediately get up and running with the full system, it increases the iteration speed of development, reducing time to market and allowing a wider pool of developers to make new classes of systems. So to fill this niche, we developed BlackParrot. We call it a base class for accelerator SoCs because we envision users taking the mainline BlackParrot code, modifying it to suit their needs, and contributing back their contribution, or configuration rather. We've designed the architecture to be flexible enough to serve in a wide variety of application settings, and we're releasing the code under permissive BSD license. However, we don't aim for BlackParrot to be the highest performance core on the market. We want BlackParrot to be small, efficient, and non-intrusive so that it fits into as many systems as possible. So when we're building this, we kind of measure our progress around 4 axes. Quality, can you trust the code? Do you trust it enough to spend money putting in silicon? Virality, we want BlackParrot to be used everywhere in academia and industry so we can convince the best designers in the world to use and improve it. Functionality, does BlackParrot do what you need it to do? Can it run general purpose code efficiently and control a wide variety of accelerators? And importantly, does it have a minimal set of features? Because unused functionality in silicon takes up area and power. And even worse, it adds complexity, increasing verification costs up to 2/3 of the cost of the chip. And lastly, efficiency. Is the code Pareto optimal in power, performance, and area? So in order to guide the development process, we create a manifesto that encompasses our 3 principles. First, we want to be tiny. We want to maintain a small, understandable code base and heavily rely on reuse from other reliable open source libraries such as Basejump STL, Berkeley Hardfloat, Google RISC-V, and others. And while we support a bunch of configurations, in order to maintain small test vectors, we only officially support a subset of well-verified golden configurations, which are likely to be used in ASICs or FPGAs. We also want to be modular. And BlackParrot at its core is a set of building blocks connected by well-specified standardized hardware interfaces. By testing along these interface connections rather than the component level, we're able to provide a compliance suite of integration tests without needing to repeatedly modify test benches. And we want to be friendly. As engineers, the tendency is to want to start every project from a completely clean slate. Instead, we're trying to leverage as many open source libraries as possible and make sure that the code is friendly and accessible to all. So now that we talked about the design and development for BlackParrot, we'll take a deeper dive into system architecture. Our development goal is not to provide an SoC generator. Instead, we're developing a reference SoC methodology and building blocks that anyone can use to integrate BlackParrot into their own system. First, we'll talk about the abstractions, which allow system designers to easily compose a functional and performant Accelerator SoC. BlackParrot can be used to build fully coherent multi-core systems with a wide range of supported accelerators. Design is not hyper-optimized to any one type of integration, but instead provides hooks to connect to accelerators with diverse programming and memory models. BlackParrot supports traditional messy type coherence schemes for using a novel protocol, which we call Bedrock. Bedrock decomposes the system into local cache engines, LCEs, and cache coherence engines, or CCEs. Bedrock is race-free by design, and it leverages 3 physical networks to support multiple concurrent coherence transactions. LCEs provide core-side connections to the memory system, and importantly, they're extremely simple. For compliance, LCEs are only required to send requests for missing memory blocks and respond to a small set of invalidation and transfer instructions. Distributed CCs maintain coherence for the subset of the physical address space and are backed by a non-inclusive L2 cache slice. CCs are a more sophisticated engine. By centralizing the complexity as a whole of the entire protocol is dramatically reduced. Because all protocol logic and method processing happens at the CC, the LCs remain very simple. And you can see this in the fact that it's extremely, it's much easier to verify Bedrock than a traditional messy protocol using an FSM. And the key here is that it's easier to use, and then it's also easier to verify so that people who are adding to the system can add and be sure that their changes do not affect the core protocol. BlackParrot is designed for a tiled network-on-chip-based SoC, which provides efficiency and scalability benefits. The Bedrock network connects all tiles in the system in a 2D mesh, and the memory network connects, of course, to DRAM. The networks are all wormhole switched and dimension ordered, which allows designers to quickly modify the link size and protocol parameters to trade off between congestion, bandwidth, and latency. And the 2D meshes work extremely well with hierarchical CAD flows because they regularize timing paths and remove most of the logic from the top level. So let's take a closer look at the tile types, which may be needed for a complex SoC. It turns out we can separate BlackParrot tiles into 4 broad categories. Core tiles are the most basic tile type, containing a single coherent core of a BlackParrot multicore, along with the uncore components needed to communicate with the rest of the system. Streaming accelerators, or I/O tiles, do not cache coherent memory, but instead stream data to and from cores through uncached requests. They can be used for everything from a fixed function accelerator to an integrated GPU. Coherent accelerator tiles contain accelerators which cache coherent memory, allowing fine-grained communication between general-purpose compute and acceleration, useful for cooperative workloads. And we can also scalably extend the size of the L2 and directory tags through L2 extension tiles, which can provide a higher memory-to-compute ratio. Now we'll zoom into a BlackParrot core tile and examine the uncore components that enable easy integration. Core tiles are the basic BlackParrot building blocks. They connect to the outside world through the open source wormhole routers provided by Basejump STL. Wormhole concentrators provide one-to-n arbitration so that multiple components in a tile can communicate with the Bedrock network on a single router. A CCE maintains directory tags for a slice of memory, managing coherence among all tiles in the multicore. LCEs service misses and invalidations, which can come over the Bedrock network either locally or from other tiles. And BlackParrot's deeply integrated L1 caches and a slice of distributed L2 cache provide high performance on tile memory. And the very last thing is the actual BlackParrot core logic. This isn't only custom logic in the tile, everything else could be repurposed for other tiles. And in fact, even other cores. Now that we looked at the uncore components in a BlackParrot tile, we'll look at how we can compose different tile types in our taxonomy. L2 extension tiles maintain coherence directory tags with a standard CCE, but pack the rest of the area with pure L2 cache. Coherent accelerator tiles have a standard LCE, but a simpler IOCCE, which manages local scratchpad memories and configuration rather than global directory tags. Streaming accelerators reuse this IOCCE, but have no need for a coherent LCE. Instead, they may communicate over the I/O network or simply perform computation and return results. BlackParrot has several levels of accelerator integration available. Because all true coherence state is managed by the CCE, in order to attach an accelerator to the network, it need only be able to generate requests and respond to commands over the Bedrock network. So a system designer using a streaming accelerator just needs to respond to these simple request-response pairs. For a coherent accelerator, a designer can reuse BlackParrot's LCE and data cache, transducing the accelerator's memory interface into BlackParrot's cache request structure. If a designer wants more control over the specification of the accelerator cache, they can use a completely custom cache that complies with BlackParrot's cache service interface, reusing the same LC as the rest of the BlackParrot system. And last, designers are free to implement full custom accelerators, which obey the simple LC functionality required by the Bedrock protocol. This option offers the most flexibility, the trade-off of longer development times. However, the modular nature of the system means that starting from an existing accelerator, the designer could incrementally customize each level of the system while maintaining functionality and testability at each step. So now that we've discussed system architecture, we're going to dive deeper into the core microarchitecture. The BlackParrot core itself is implemented as an 8-stage single-issue in-order pipeline with a 2-cycle iCache and Dcache access time. It features a BTB, BHT, and return address stack for branch prediction and a non-stalling, statically scheduled backend. By having a single stall point and single commit point, this prevents large enable fanouts and costly dynamic write-back scheduling. Rather than traditional FSM-based directory controllers, the Bedrock engine and BlackParrot are the first open-source programmable cache coherence engines. The CCE runs a custom RISC ISA with a specialized protocol operations, such as looping over LCEs for bulk invalidations or scanning directory tags in parallel. At boot time, microcode is loaded into small CC instruction RAMs, allowing modifications to coherence policies on the fly. This means that you could add security patches, coherence debug modes, or performance monitoring functionality after you've taped out your chip. And all these building blocks are connected by clean and narrow interfaces. Unlike in software, these interfaces have physical manifestation, so large or underutilized ports can seriously impact PPA. By defining the interfaces minimally, but allowing for extension, developers on any component of the system need only focus on adhering to the interface, rather than worrying about the implementation of details in of the components. This speeds up both front-end and back-end development as both functionality and timing paths are isolated. Importantly, these interfaces are latency insensitive and flexible. BlackParrot configurations can seamlessly substitute different implementations, such as a scratchpad-based front-end or traditional FSM-based CCE. So now that we've talked about BlackParrot as a host core, we'll describe an ongoing integration in our lab. This is using BlackParrot to control the Hammerblade RISC-V Multicore. So first I'll introduce the Hammerblade supercomputer, which is a RISC-V ASIC that's focused on aggressive scalability. It uses a massive array of area optimized tiles to perform highly parallel computation. It's highly programmable, leveraging popular frameworks such as PyTorch, TVM, and Graphit, as well as a familiar GPU-like programming model called CUDA-Lite. Hammerblade is designed to scale from a single ASIC to an array of cabinets, performing massive computations. And while Hammerblade silicon is capable of massive parallel processing, it currently relies on x86 host core to coordinate its activities. Namely, applications like PyTorch, TVM, and CUDA-Lite are all compiled for the host Xeon, which communicates through the Multicore over a narrow Multicore bridge. This Multicore bridge comprises a set of memory-mapped FIFOs, converting from the host link to a standard Multicore endpoint, which communicates with the Multicore network, managing the credit-based flow control and preventing deadlock. However, this approach loses substantial performance through what we call gearboxing. Because of a 32-bit AXI bus, each memory request is actually composed of 4 packets. Disjoint memory address spaces means there's a separate memory management runtime, costing performance and programmability. And lastly, needing to synchronize on the far side of a PCIe bus means that bandwidth between the systems is ultimately constrained by the bus latency. So let's look at how we can leverage BlackParrot's flexibility to fill these gaps. Because BlackParrot is open source and customizable, we can quickly prototype different settings to optimize system performance. We can place BlackParrot and Hammerblade on the same piece of silicon, which prevents these exorbitant off-package and off-die link energy costs. Since both designs are on the same die, we can add hardware blocks directly between the components, which allows cycle-level communication acceleration between the two cores. But there is a downside. As I mentioned earlier, BlackParrot isn't competing with the Xeon. Instead, it's focusing on energy efficiency. But it turns out that this is really unimportant for the system as a whole. Host management code is not the bottleneck in heterogeneous cooperative workloads. Data shuttling, shuffling, and synchronization dominate in terms of system performance, which means that with a very minimal efficient core, as long as we tweak workloads and accelerators to shift the burden from compute to communication, we can achieve peak system performance. So with this trade-off in mind, we've designed the host API for BlackParrot to support multiple types of traffic patterns. For bulk transfers, packets are formatted for the many-core network in software and then sent via non-blocking stores. This allows the most direct access to the many-core network. Similarly, load responses from the network are enqueued into a host FIFO, which can be claimed by any BlackParrot core using a side-effecting load. A new type of request is direct MMIO from BlackParrot to the many-core. By embedding the 32-bit many-core address space in BlackParrot's 40-bit address space, BlackParrot loads and stores can be directly converted to many-core addresses, meaning no host code is necessary to construct the many-core compatible packets. This means that host code can be written with shared pointers, and you can do direct interactions with the many-core network with single cycle throughput. So this is a diagram of the HammerParrot prototype. The improvement that you see here is that we've replaced a single serializing many-core bridge with a set of parallel bridges. This allows bandwidth scaling proportional to the number of host cores. The many-core bridge looks similar to the x86 hosted system, except with the gearboxing removed to allow for more efficient direct accesses. We can see the host request, host response, and many-core request FIFOs are identical to the x86 counterpart. We add a reordering FIFO to allow for returning request packets to their source in the case of non-point-to-point multi-core contention. Now, with the addition of these reordering FIFOs, the links are extremely scalable and can be replicated across the rows of the many-core. Each link could be configured to maintain a single tile group of the many-core, or each have access to the entire array, depending on the expected memory access pattern. The HammerParrot system will support high-performance direct and burst traffic, gigabytes of scalable throughput, starting from 32 bits per link per cycle, with up to 32 outstanding low latency requests per link and configurable burst traffic capacity. This is a system which can tear through traditional CPU, GPU style workloads, as well as support more unique heterogeneous cooperation, enabled by the open source BlackParrot and open source many-core projects. So now we've talked about BlackParrot a lot in the system architecture. We've looked at example system application. So we'll talk about how we're trying to build up the BlackParrot flock of users and developers. And the first thing is that we're trying to encourage users to become developers. We want people to be able to use BlackParrot for their needs and then be able to modify it to suit whatever improvements need to be made. We want BlackParrot to be directed by community consensus rather than controlled by just one group. The second thing is that we're building the infrastructure with community in mind. We're using open source CAD tools and open source simulation tools as soon as they're available. And we're striving for infrastructure agnosticism so that people can just simply download code, press a few commands and make possibly, and then have a tape out ready ASIC in a handful of commands. We validated BlackParrot and FPGAs. We've synthesized and tested on a variety of Xilinx FPGAs, and we've integrated BlackParrot to LiteX, which is an excellent open source Python-based FPGA design environment. We're excited about this integration as it will instantly give BlackParrot users, or LiteX users, access to BlackParrot without having to do much configuration at all on their end. BlackParrot's also been silicon validated. A 4-core BlackParrot was taped out in GF12, July 19, and it's back and running in the lab since April 20. BlackParrot's been ported to TSMC 40 and 345 PDK nodes. This is a process agnostic design. It's been silicon validated over a variety of modern tech nodes, and will continue to use PPA improvements based on these tapeouts. So describing this BlackParrot ASIC that was taped out last July, it was a prototype 4-core BlackParrot, and lessons learned from this tapeout allowed us to reduce area, power, and routing by up to 50% in the most recent version. Even tool runtime was cut in half by more aggressive modularization and distribution of resources. And this just shows how important it is to actually go through the process of taping out a chip when you're doing research. These were issues that we couldn't have possibly found in simulation and only come up when you go through the full process of placement and routing. So not only is BlackParrot's RTL open source, we also openly develop our tape out builds. This includes things like placement scripts, lists of hardened memories, and block shaping information that are needed for good quality results. All the BlackParrot tape outs past and future are hosted at this website, and we hope that external system developers will also contribute so we can build up a suite of reference designs for BlackParrot in the wild. We also participate in Open Road project as a test case. This is a new open source push button CAD flow which aims to compile from RTL to GDS in 24 hours. With Open Road, FreePDK45, and BSG FakeRAM, today you can push BlackParrot all the way through a fully open source CAD flow and go all the way to GDS. So BlackParrot's already starting to take off. We're using it as a teaching tool in several graduate classes. Dozens of features and enhancements have spun out from student projects. Several student developers contributed back to the mainline. And each iteration of teaching has highlighted and helped patch infrastructure weaknesses, added quality of life enhancements, and documentation gaps. We hope to get BlackParrot into as many hands as possible, in classrooms, academic research, and in industry. We've integrated several other open source projects, including LightX, OpenPython, OpenRoad, Dramaggio, and more, both to leverage for our own development and as a method of testing and demonstrating BlackParrot in as many environments as possible. So that's BlackParrot, the Linux RISC-V capable multicore. It's silicon validated, it's ready to be included in your next lightweight accelerator project, and we're excited to see the unique systems that BlackParrot proposes in coming years. Together, we can make BlackParrot the global default choice for RISC-V cores. So yeah, it's great to be here virtually at this workshop. So I'm excited to collect ideas from everybody, from the HPC community of where can we improve, how can we use BlackParrot, what kind of systems could be leveraging this. So yeah, I'll take any questions now and feel free to contact me for any follow-ups.
Thank you, Dan. That was a great talk. Really appreciate all the insights and components there. If you have questions, please add them to the Q&A tab so we can go through those. One of the first questions from Roberto, which was not in the Q&A tab, is you were describing 3 different NOCs that are completely packetized. Why not just use a single NOC with traffic control, maybe QoS, quality of service, for the 3 types?
Sure. Yeah, that's a great question. It really comes down to complexity. For first, the Bedrock network with its 3 networks have a static prioritization scheme between the 3 channels. So you're able to guarantee that you're deadlock free as long as you follow these very simple protocols. The second reason is that between the memory IO network and Bedrock network, there's different constraints and different optimizations you can make. For example, in the BlackParrot chip that we taped out, our memory network was only a 1D network because it only had to go down to where the DRAM controller was on the chip. So you can save on entire direction and routing for that. So it's good to have this kind of orthogonality, but you could certainly combine them in your own physical implementation. Very cool.
Second question from Roger Espasa is, was the 12 LP tape out done using OpenRoad or commercial tools?
Also a great question. That tape out was done using commercial tools, only because the OpenRoad project was still pretty nascent at that time. But there are upcoming tape outs that will be using OpenRoad.
And do you have a sense for what, just a follow on for more clarity, what nodes are going to be available in the upcoming OpenRoad tape outs?
I'm not sure I can answer that or know how to answer that.
More the question of which, is 12 LP going to be supported, 28 nanometer?
Yeah, 12 LP is the goal for like the target that we're using for like calibrating the tools and things like that.
Awesome, fantastic. Next question from Dr. Ali Ahmed. Have you guys used all open source software from design to tape out, or are you using proprietary software? And I guess this is more along the OpenRoad side.
Right, yeah, so that we have used commercial tools for the actual tape out from synthesis to GDS. We do run using OpenRoad internally for just to validate that the flow works. And then for simulation, we support both VCS and Verilator. So when we run our test regressions, we make sure that works in both. And we've actually uncovered half a dozen bug fixes to Verilator that we've contributed back to make sure that it keeps working, which is a pretty cool contribution.
That's awesome. Another question coming over the chat. Will your, I guess, I'm not sure if this is BlackParrot or the actual accelerator you're building, does that support instructions required for neural nets? Are you doing low precision, tensors, those types of things?
That's a great question. The Hammerblade, let me go back. The Hammerblade Multicore itself is a heterogeneous mesh, so it can support many different kinds of tiles. In the past, you can look up Celerity was the previous version of Hammerblade, and it had one layer of these RISC-V cores, these like very tiny area optimized 32-bit cores, and then it had a large array for neural net processing or graph processing, more to the point. So I'll say the infrastructure itself is designed so that the tiles can be tailored to whatever you need, even possibly using FPGAs within the mesh to reconfigure what you need.
Nice. And then I guess the other types of things would be interesting to comment on are, do you support any SIMD or vector-like operations in the Hammerblade?
Not currently. So currently each tile runs its own thread of a RB32i like vanilla core processing. And the idea here is that these components like PyTorch and TVM are able to map into the backend as a single GPU thread like that. So this mapping works really well. But if you start splitting up SIMD within that, the tools don't really know what to do with that because you're almost parallelizing too much. And our answer is just add more cores.
That's a fine answer. We'll see how that works. So fantastic. There is time for maybe one more question. If not, we will continue on. Dan, thank you for a fantastic talk. Looking forward to seeing more great stuff from you guys and Mike and his team. Let's move on to the next piece of this. So next up, our talk is Andrea. He's coming from, he's a professor at the University of Bologna in Italy. He received his PhD in electrical engineering from the University of Bologna in 2011, where he currently is an assistant professor. He did his postdoc work in the IIS laboratory at ETH in Zurich. He has over 100 papers in peer-reviewed international journals and conferences with a focus on energy efficiency and embedded and HPC systems. And with that, Andrea, please take us away. And you're on mute, sir.
Let me share the screen. Yes. Okay, can you see my screen? Okay, assuming yes. So,
yes.
So my talk of today is going on updating on the recent achievement and development from the Pulp team in supporting the HPC open hardware scenarios. And my background is more on energy efficiency, so I'm coming top down on the HPC system. So I've been working in the last years on creating HPC clusters that have been ranked on top 500 with several achievements on OpenPOWER systems, such as the Davide system installed in Cineca in Italy. And also in these days, I've been working also in the team that has designed the Marconi 100 system, which is ranked in 9th position in the top 500. And I'm gonna show you today most of the work that is not done by me, but by the folks in ATH and Unibo laboratory working on the design open hardware. And so by starting, why, and the talk of today is about really seeing how outcome of the PAL project can be really a Swiss Army knife for creating an open hardware and open source HPC processors and system. So the the first important from this slide, the first thing that we can see is the challenge that we are facing moving toward exascale. I know that this slide is common to many of you, and it's good to remark that today high-performance computing systems are power-bound, and there is every 4 years there is an achievement on 10x energy efficiency improvement, which led to have an increase in performance. In the plot here, we can see that with blue dots are the performance of the fastest supercomputer worldwide, so the ranked first in the top 500. And in green, we see the energy efficiency computed as energy per operation for computing a double precision floating point operation on those systems. And we can see among time that the energy has decreased, and that have led an increase in performance of the installed system. What we can also see is that for achieving an exaflop machine, we need to be capable of computing a double precision floating point operation with 20 picojoule of energy consumption. And this comes from the fact that it is assumed reasonable to have a supercomputer which consumes 20 megawatt and no more of that. So if we look at the HPC trend, so if we want to achieve a performance of 1 exaflop, so 10 at the power of 18, we need to have 10 at the power 18 double precision floating point operation per second. And due to the stop of Dennard scaling, we have that we can clock a floating point unit at maximum gigahertz speed. We cannot go faster. And this means that we need to have in our system 10 at the power of 9 floating point unit, double precision floating point units, if we want to build an exascale system. And which means also that we need to have an application parallelism with a serial fraction of 1 over 10 at the power of 9 due to Adam's law for being capable of using effectively this system. And this leads to first the fact that we are power bound, so that we are already at 20 megawatt, and by increasing the number of floating point units, the only way of increase the number of floating point units that we put in our system is to increase the energy efficiency of the floating point unit operation. As we saw before, we have to reach the 20 nanojoule per double precision floating point operation. And we also need to have good programmability support to be capable of using effectively this system, this large number of floating point unit. When we look at how HPC system has been designed in the past, historically, CPU was designed for being fast in all the workload. And this led to having a large silicon area wasted in maximizing the single thread performance. And these have led to systems which have reached the maximum power consumption allowed by supercomputing centers, so around this 20 megawatt of power. So there's been a first change in paradigm already in a few years ago, which have led to new processor in the HPC domain designed for a maximum performance only on a reduced set of workloads. We will see which one are these workloads just in a few slides. And to doing that, the design has moved to to systems with processor designed with simple functional units per thread performance, but done to maximizing the throughput. And this is foreseen as a way of achieving the required performance by staying within the data center capacity. So we want to maximize the power and the area of the silicon that we give to the floating point units. And the design are going toward that direction and reducing the wasted area in the silicon and power to other operation. And it's the second change of paradigm is that also in the HPC system, so in scientific computing clusters, there have been already a trend on starting to use new computational paradigms such as deep learning as a way of solving complex problems that before were not simple to be modeled, and also to exploit the efficiency of reduced precision arithmetic in hardware accelerators. And these slides show that already a few years ago, a first exaop application was executed on by a researcher in Oak Ridge Laboratory, so on the Summit system, which had the Volta GPU card that was capable also doing at the tensor core operation, so going faster in doing tensor core operation with respect to the precision floating point. And also there started to be ranking of the HPC supercomputer. It's been proposed the ranking of the HPC supercomputing machines also based on their capability of training models for deep learning. So these new workloads are coming, and they're always more important. And the third change of paradigm, which is also been already discussed before, is the fact that the system are power bound, and we can see it in this slide. So this is slides taken from the academic discussion group, the OpenPOWER academic discussion group in 2018, which was reporting an unexpected behavior of the Summit processors, of the GPUs inserted in the Summit processor. These were the Volta V100 card, for which the theoretical peak in doing tensor core matrix multiplication arithmetic was expected to be under 25 teraflops, and they measured actually a almost close to the theoretical peak performance of 113 teraflops achieved when the matrix that were used for doing the multiplication were zero field matrices. And this performance was decreasing if the matrices were filled not with zero values, but also with random numbers. And if the numbers were even more random, the performance drop was decreasing down to 95 teraflops per second. And so the performance of the system is dependent on the numbers that you are multiplying in your tensor core operation, which is unexpected. And then why this was happening, the fact is is reported on the two plot below, and let me just take the laser pointer. So in the two plot below, on which we can see that in blue line is the power at when we have random numbers, and in orange is the power when the operation was done on zero values matrices. And what we can see is that the frequency of the Volta card was decreasing with when the operation was done on random numbers, and this was due by the fact that the power consumption, so the effective capacitance of doing the computation on zero values, was lower than doing computation on random numbers, and this was leading the power consumption of the card to hit the maximum power budget allowed on the system. I remember that the system is liquid cooled, so pretty efficient, and so the frequency was reduced to do not overpass this power budget limit. And so the systems are, an HPC system is not only about energy, but it's also about handling the peak power consumption during operation. And we will see that in the later slide that we tackled it with the PAL project. And finally, the last change of paradigm is the fact that there is not only the processors, but there is also the system integration, for which there is an ongoing trend to try to ease the complexity of managing a supercomputing machine by leveraging IoT big data infrastructure to create feedback loops which can autonomously manage the system, and this the system administrator works. And so also the processors needs to be designed to have a flexibility to allow this. So coming to the talk of today, so within the PAL project, can it be an end Swiss Army knife for opening the path toward exascale? And to do so, we need several tools. So the first tools that has been developed in the PAL project has been the Ariane core. These are all open source and publicly available components, the one that IPs that I'm going to discussing now, and you can find them in the PAL platform website and Git repository. Some of them are not yet released because they're really new, but they're going to be released soon. And as I said also at the beginning, this is not my work, so I want to acknowledge the developers and the true students and postdocs and researchers that have done this work. So I'm just presenting them organically. So the Ariane is the 64-bit application processor, and it's capable of booting Linux, and this is the first component that has been built in the path toward high-performance computing system derived from the PAL project. Then we have the NTX, which is the Network Training Accelerator, which targets directly the training of neural network models, and this is an IP which is designed for increase the utilization of the floating point unit with a reduced numerical precision formats, which is handy for this computation. Then there is the ARA, the vector engine. So it's a configurable floating point vector unit. We have also the SNITch, which is an evolution of the NTX framework, which is a pseudo-dual issue processor for a floating point intensive workload. And through SNITch, we achieved a really high utilization on the floating point unit with a really reduced area overhead for supporting flexibility in the programmability of the of several workloads. Then we have, of course, there is not only hardware, you need also to program, and if they are accelerator, you need to program in heterogeneous matter. And this goes to the Hero, which is an open source heterogeneous research platform, which actually targets the offload of computational kernel on accelerator, on tightly coupled accelerators, and sharing of which shares together with the host shared memory, so they can exchange virtual pointers. And then finally, we have the Control Pulp, which is a power controller for HPC server processor, so allows to control the power consumption and the temperature evolution of your system and interfacing with the system. So I'm going fast on the different components. So as I told, Ariane is a RISC-V 64-bit 6-stage processors with in-order issue and out-of-order execute. It has internally a transprecision floating point unit, which is capable of reduced precision format numbers. So it supports double, single precision floating point formats, and also two customs, FP16 and FP8 numerical formats, and which can be all of them used in SMD fashion. There are two implementations of Ariane. One targets high performance computing, the performance domain, and the other is single thread application, and so the low performance domain, higher energy efficiency. Ariane has been together with thanks to the OpenPython project, has been integrated in a many core system, cache coherent many core system, so can be instantiated in the many core system. And then we have the Network Training Accelerator, the NTX, which is a streaming coprocessor, a 32-bit floating point streaming coprocessor, which targets indeed the network training. And the idea of the design of NTX is to reduce the von Neumann bottleneck by streaming paradigm, and also hiding the memory, the DMA latency by using double buffering. And it is composed by a processor with a controller and and a number of processing engines. So there is as I was saying, there is a processor core which controls 8 NTX coprocessors, and all of them are connected to a 128 kilobyte TCDM memory connected through logarithmic interconnect. There is a DMA for engine to transfer the data supporting double buffering, and different cluster can be connected, different NTX cluster can be connected together through a crossbar or a network on chip interconnect. If we go a little bit more inside NTX, we have that it's configurable by the host processor by writing commands inside its own memory, and then it has an address generator which can generate the stream memory accesses, and then it has supports a fuse multiply add with extended precision plus hardware machine learning function, and has two ports to the memory. And as I said, and it also supports low bit with floating point formats support numbers. So it's interesting to see how NTX and Ariane compare between themselves. So last year has been taped out a Cosmodrome chip on 22 nanometer FDX technology, which was having inside both two Ariane processors, so one targeting the high performance domain region and the other the low power region, and also an NTX cluster. And so when we compare NTX and with the Ariane processors, the first thing that we can notice is the fact that the efficiency of that the peak performance of NTX is about 24 gigaops per second on 32-bit floating point numbers, matrix multiplications, and while Ariane, it's limited to its clock speed is a single core, so it can achieve 1.5, 1.3 gigaflow per second. The efficiency of NTX improve of 18x the speed in doing 32-bit floating point operation with respect to Ariane, and the energy efficiency is higher for and the energy efficiency is higher with of 6x with respect of Ariane for NTX, reaching 266 gigaflops per watt as energy efficiency, which is double more or less of the energy efficiency of a Volta V100 in doing tensor core operation. So NTX can really improve the efficiency of 32-bit floating point operation. However, is not capable of 64-bit floating point operation, so double precision floating point operation, which are a need for exascale system. So an answer for that is the ARA, which is an open source RISC-V vector engine, which can be tightly coupled to Ariane, and it's been designed for a target of 0.5 double precision floating point per byte computational intensity. And but the computational capability can be configured by increasing the number of lanes of the vector process of the ARA vector processor. So if you look at a matrix multiplication kernel done with ARA, we have that we can execute one vector multiply add instruction every 4 instructions, and which leads to the fact that since Ariane is a single issue, we have the fact that in case the vector multiply add takes less than 4 cycles to execute, the floating point unit will have to wait for a new instruction, so it will hit the von Neumann bottleneck. On the right plot here we have the roofline plot of ARA, and we can see that by configuring the number of lanes, this is L on the plot, we can increase the peak performance of the ARA vector processors, and which its theoretical limit is depicted on the picture. And with dots, we have a real measurement of the computation which can be achieved by running matrix multiplication kernels of an increasing number with an increasing n, moving to the right. And we can see that as also is expected for vector units, that by reducing the matrix size with respect of the peak performance capability of the vector processors, we have inefficiency due to the fact that the vectors become too small. And so ARA has been taped out on 22 FDX Global Foundries technology, achieving 1.25 gigahertz in performance. And the important numbers are here on the bottom, and we achieve an efficiency in doing double precision floating point operation of around 38 gigaflops per watt, which is roughly 2.5x better than Ariane on the same benchmark. The peak performance of ARA, if configured with 16 lanes, is of 40.8 double precision gigaflops over watt in efficiency, and of 32 double precision gigaflops per second. Then we have an evolution of the NTX and also FARA, which tries to increase even more the area which is spent in floating point operation, and also the time on the code that is what we spent in doing floating point operation. And this is called SNICH. So SNICH is a pseudo dual issue processor for floating point workload. So it takes care of on the side of SNICH, we have a floating point unit which are tightly coupled. So SNICH can do the integer and all the address generator, while the floating point unit can do the floating point workload. Then the SNICH are organized in clusters, and every 4 SNICH core complex, we have a shared multiply divider and instruction cache among the 4 SNICH core complex, and which is called hive. Then we have that 2 hives shared a TCDM memory and peripherals, which realize a cluster, and then the end cluster shares a crossbar and access to the system memory, to the main memory. And so the novelty in SNICH is the fact that SNICH uses 2-stream semantic registers, which allow to realize memory access as if they were register access, and also an FPU sequencer. So if we look at how SNICH can be used for doing a dot product, so the idea is to be capable of increasing the semantic of SNICH such that we can program once, and SNICH can directly generate the addresses and loop over instruction, and also keep while the floating point unit is active, the SNICH core can still feeding in parallel the floating point unit. So we have a pseudo dual issue processor. And so when we look at SNICH compared with ARA that we saw before, SNICH is really small. If we see a core complex, which is here, the area of SNICH is really small with respect of the floating point subsystem. So it does really a small overhead to floating point cores, but it has a really high flexibility. And this can be seen when we compare SNICH against ARA in several configurations. So a number of floating point unit for SNICH means the SNICH core complex instantiated in the cluster, and for ARA means the vector lanes. So the SNICH, and here is the dimension of the matrix multiplication, and we can see the SNICH really achieve a higher efficiency, computational efficiency with respect of ARA, both in small vector than in large vector, and with small configuration and long configuration of the computation. Moreover, when we look at the performance, the SNICH is capable of achieving on 22 nanometer FDX technology almost 80 double precision gigaflops per watt in performance, so twice the efficiency of ARA, and leading to a 30 picojoule per double precision floating point. So it's already ready for exascale computation. And this is thanks to its flexibility. But then we need to program these accelerators, and this is and the problem is to be capable of sharing code efficiently from the host to the accelerator with the shared memory accelerator. And to do so, in the lab has been developed the HERO support, which is an heterogeneous research platform which today supports 2 toolchain, which are the ZCC and the LLVM toolchain, which allows to share pointers between the host and the coprocessors. Finally, we have control pulp, which is an extension of the Pulpissimo system to support the control of the power control of high performance computing systems. And indeed, in a high performance computing system, there is the need of controlling the power consumption during execution of the processors, and the controller needs to interface with operating system, application system management, and also in the motherboard with voltage regulators, memories, and also board management controllers. So control pulp is designed to support all these interfaces and to handle the operating point of your many core systems in high performance computing domain. And this is done by also having a firmware which really allows you to do all these tasks efficiently. Finally, all these components and IPs that I've depicted are converging and are pushed by the European Processor Initiative, which is fostering the evolution of and the design of these hardware components. And so to conclude my talk, we saw that really through the PAL project, we can really have a really wide set of tools which can allow to build an exascale system already today.
That was a fantastic talk, Andrea. Thank you very much. Great overview and obviously focus on the high performance side. If you have questions, please add them to the chat. The first question that is from Jisen is the ARA vector engine open source? And if so, is there a GitHub repo link that you could provide?
Yes, so ARA is open source and is available in the GitHub repository in the PAL platform. So you will have in the afternoon a talk from Frank from ATH Zurich, and he will describe you how to get access to the IP, to open source IPs.
Fantastic, thank you very much. One of the questions was looking at the DMA and what is the achievable performance of that for the NTX cluster? Andrea, we cannot hear you for some reason.
Sorry, I was muted. So the snitch can execute at 1.55 gigahertz frequency, and you have 2 memory ports. So the bandwidths can be computed by these numbers, and there is a paper on that. So on the Cosmodrome, which there are more details.
Great, thank you very much. And one final question, obviously this is impressive work. I think everyone will say that, so congratulations you and the Pulp team. There's one question about, curious to know more details about the SSR streamer. Can you provide some pointers to that?
So there is a paper on snitch which you can find on arXiv, and there you can find more detail on the semantic registers, on the stream semantic registers.
Fantastic. Again, thank you very much for a wonderful presentation. Looking forward to hearing Frank's talk as well. We will switch on to the next one.
Shall we stop sharing? Thank you everyone for listening to the talk.
All right, that's fantastic. So the last talk for this session is from Anton and Tristan. Let me give a quick intro to these guys. This is going to be focusing on OpenPOWER. Anton has been involved with Linux and open source software for over 20 years. Much of that time with IBM. He leads a worldwide team dedicated to using open source technologies to build better products. In mid-2019, he got the open hardware bug, and as a result of IBM's opening of the Power ISA, so we'll be talking about that. Tristan is coming to us from CERN. He has developed GHDL, the main open source VHDL simulator, for about 20 years, and he's in the hardware and timing section at CERN. So with that, gentlemen, I will let you guys take over. Looking forward to a great talk.
Thanks, John. I'll just bring my charts up. Is that coming through okay?
You can see it. Thank you.
Great. So yeah, we're going to talk about two things today. I'll be talking a bit about a core we've been working on for the last number of months called Microwatt. And Tristan's also going to talk about GHDL, so a little bit about open source VHDL simulation and synthesis. Just to kind of set the scene, obviously most people would know the power architecture has been around for quite a while. I think, John, you mentioned Mare Nostrum in 2004. I was one of the lucky ones on the IBM side to work with the team at BSC on one of the early Linux supercomputers, and it's been a lot of fun. Just more recently, obviously, Summit and Sierra are no longer 1 and 2, unfortunately, but still way up there. They're all power-based, so yeah, we're building big supercomputers based on the power architecture. OpenPOWER has been an effort over the years to start opening up the architecture, and that started mainly at the system level and the software component level. So we're talking about things like system designs, but also things like firmware components. So some of the software stack that goes towards it. Looking at the firmware stack, our systems are one of the only in the industry that are completely open source. Some of our systems have a completely open source stack from top to bottom, bottom to top, depending on which way you want to look at it. And so if you look at everything from power on through to Linux booting, and then obviously things like KVM hypervisors through to user space, everything is open source and available on GitHub. And so that was the progression. We're talking system designs, we're talking software. The next logical step, well, I mentioned one thing before that. We also have a partner that works on a design that's built around owner control computing. So again, having access to all of the software that runs on your system. It's Power 9 based. It's a native desktop environment for using that whole open source stack. Now at that stage, the next logical step was to look at what else should be opened. And back in August last year, that was where IBM decided to open up the architecture. And so I was involved around some of the decisions around opening architecture. And at the stage, we were also talking about, what else can we do? And what were some of the ideas that we could bring around the announce. Few points on the announce just quickly. It was basically, an announce that obviously, yes, it's now open. It's royalty free. It is also inclusive of patents. So some thought has gone into that. The foundation now moves into the Linux Foundation. And as I said, the little bit of thinking we had was let's build something. And as a background, I'm actually mostly a software person. I work very closely with our hardware teams. But I thought it was a good opportunity for more software-based or software-focused people to really get involved with hardware and give it a try. So Microwatt is kind of the output of that. So what is Microwatt? Well, it's basically it's a tiny power core. It's 64-bit power core. It uses what we call the open ISA scalar subset. And in fact, Brian Tomto later today will be talking a bit about the ISA subsets and how we've chosen to carve them up and the like. It's written in VHDL 2008. Now inside IBM, we have a lot of designs and we have a lot of Verilog and we have a lot of VHDL. Outside of in the hardware, the open hardware world, I should say, Verilog has been, more of the focus. And we were interested as well to kind of push on, the open synthesis and simulation space in VHDL. So it's a VHDL based core. We worked very closely with Tristan on things like simulation. So we're using GHDL for simulation. The other thing we're using more recently, and Tristan will talk a little bit more about, is the ability to do open source synthesis for FPGAs using GHDL, Yosis, and NextPNR. So that means you can take your VHDL and use a completely open source flow, which for us has been really interesting. And I'll touch on it a bit later, but coming from the open source software world, one of the important things has always been to be able to easily test and build and reproduce, environments, have CIs running on, random areas, for example, in GitHub. And vendor tools don't often lend themselves to that. So, apart from the fact that, from my perspective, I can go in and look at everything because it's all open source. That's fantastic. But just the logistics of being able to automatically test and all that kind of stuff was a problem for us until we had the ability to have a full open source flow. And the GitHub link is up there. Just a quick overview, nothing really interesting. It's a pretty usual single issue in order queue core, I should say. The idea is it aims to be simple and easy to understand. And one thing that we really wanted to do was try and reuse from the open hardware world where possible. And I'll talk a little bit more about it, but things like UARTs and DRAMs and Ethernets, there's no sense in us making them ourselves. So, why don't we go and reuse them from the open hardware world? As I said, it's on GitHub. It's out there. You can pull it. You can type make. We also support Docker as a target, so you don't even need to install all the tools. They can all be pulled in by Docker or Podman, depending on your distro. We basically work within the GitHub environment, including the CI. A little bit about language support. As I said, this is something that's just come on the scene since August last year. One of the reasons we were interested in trying this was that we could really leverage the ecosystem, the PowerPC ecosystem. One example is I use my distro toolchains for my development work. Over time, we've been able to take stuff that already runs on our power systems and kind of get them running on Microwatt. We started with MicroPython. That's a great little Python interpreter, really simple, runs on an amazing array of things. That was a pretty easy port. We then went into Zephyr. Zephyr is a really interesting IoT OS. And so it supports a wide number of platforms, but that was kind of an interesting stepping stone. Along the way, we had a contributor just pop up and ported Rust. And so the embedded Rust environment, and again, went on quite easily, which was good to see. After that, we went for a walk on the weird side. Someone ported Forth. Okay, it's not my cup of tea, but they managed to get that going. That was interesting. And then finally, we kind of got back in line, and more recently, I've got Linux running. And I mean, that was always an aim for us. Myself and some of the people that are working on Microwatt are Linux kernel developers, so we were always keen to get Linux running, and so now it does. It is pretty small. This is just an example of LUT usage over time, and this is a bit of an FPGA metric. These are actually Xilinx Series 7 LUTs, but in the scheme of things, it started off a little big, and it got better over time as we I would say learn a bit more about how to write efficient hardware. I guess coming from the software side. It took a bump at the end, but that was when we added things like an MMU and caches. So it was kind of expected. But in the scheme of things, it's tiny. Some of the recent developments, I was talking about code reuse, or I should say hardware reuse. LightX has been very interesting. So we've been working very closely, or Ben Herenschmidt has been working with Florent around integrating into LightX. And that gives us a lot of stuff for, well, not quite free, but almost free, things like DRAM controllers and Ethernet and the like. So that's been very useful. Over the last couple of months, caches, branch predictors, interrupts, and TLB have been added by Ben, Paul, and Mikey. And that was all leading up to obviously running Linux. And so Linux now runs thanks to a lot of work from Paul. Another key component of what we've been doing is continuous integration. And so I mentioned the fact that, we link in with the GitHub CI. So basically every commit that goes through has an automatic set of tests. We know we're not going to break the main line when you decide to pull something in. And on top of that, we've had many community contributions. People out there have given it a go and been able to add, maybe instructions or little bits and pieces that may have been missing. So it's been fun so far. We use the CI, so this is an example here, pretty simple. Every check goes through a bunch of testing using the GitHub CI. Back on hardware reuse, you know, that's been, I think, a success story for us. We're using the Wishbone bus. It's a simple bus, but you know, probably I would say a good design point for the FPGA space. It's simple, it's an open protocol, and it is widely used. And for us, it's been great because you know, we've really got a lot out of the LightX project. So that provides a bunch of, you know, interesting IOs that we can hook up to things like DRAM and Ethernet. And it means we don't have to build them ourselves, which is fantastic. And I think there's going to be much more to come along those lines. Now let's talk a little bit about open source simulation and synthesis. And so on the VHDL space, the premier open source environment for simulation is GHDL. It's been a great environment for testing, including our CI work. It has good language support, and it has probably the best VHDL 2008 support out there. We've now dealt with all the vendor tools, and they're all broken in their own little way. You know, a bit of a plug for Tristan here. The maintainer is very responsive, which has been great. So as we've found gaps, Tristan's added that, and that's, you know, another great thing about working in the open source realm. I think the tooling improves, and you know, you have the ability for things to move quicker, I think, than maybe in the proprietary space. Now, one interesting thing that's only happened over the last few months is GHDL has actually added synthesis support. So not only can we simulate now with an open source toolchain, we can now synthesize all the way to an FPGA with open source tools. And that, again, has been really useful to us. So we can now deal with a complete pipeline of GHDL feeding into YOSIS and XPNR to synthesize for these FPGAs we're working with. The other interesting thing is, it's been kind of fun, is that you can actually do conversions. So we can now convert VHDL through to Verilog, run it through Verilator, and that works. You could also do mixed language simulation and synthesis. So these tools are moving quite quick and offering a lot of interesting new things that you couldn't do a few months ago. One thing I'll mention is this is addictive. I started with one FPGA. Now I have a desk full of them. I'm just looking down. They're filled with FPGAs, and so it's kind of one of those spaces that once you're into it, you know, you're addicted. So I will say, you know, if you're interested, please come along and join us. We're on GitHub, and you know, pull it, have a play, simulate it, maybe get it on an FPGA, and you know, it's been an interesting time for us as more software people getting involved with hardware, and I think you know, the time is right, and I think we'll see more of it. So having said that, I'll now hand over to Tristan, who'll talk a bit more about the GHDL side.
Thank you, Anton. I'm sharing the screen. Is it okay?
We can see it. Thank you.
Okay. So I won't talk a lot about GHDL, but I will mostly try to draw the FOSS ADA ecosystem, at least what I know about it. Sorry. So FOSS stands for free and open source software, as you may already know, and it covers software with code sources available, and for code source that can be used without any restriction, modified, and redistributed. Okay, there is a small difference between free and open source, but it's not the topic of this talk. And EDA stands for Electronic Design Automation, and that's software that maybe that has been written since the 80s and helps a lot via automation the hardware designer and electronic hardware designer. Okay, EDA is a very large area, so let's try to clarify it a little bit. So in electronics, EDA is used for drawing PCBs, which stand for printed circuit board. So it's a board that supports all the electronics. And the main project for the main open source project for PCBs are KiCad and PCB. On the different use of EDA, it's for integrated circuits, so ASIC or FPGA. And for, let's say, pure ASIC tools, in addition to the newly open world, we can name Coriolis, which is a place and route tool, and the Kubeflow and Magic tool. And in between, I will just mention quickly analog tools, which can be used either for PCBs, because you want to simulate how signal propagate on a board, or for analog ASIC. And let's say some of the tools which are known are Pux for circuit simulation, and ngSpice, which is derived from the well-known SPICE tool. So let's focus on integrated circuit. Basically, for numeric integrated circuit, it's they contain an ocean of gates which are used to do computation, flip-flop and latch, which are used to memorize bits and data, and also to synchronize the signal propagation. Memories, which are used to store a lot of data, and are also always even on a pure numeric circuit, there are always many analog components like PLL, so to multiply a clock, to increase the speed of a clock, and also to control the paths of the input and output from the circuit. And when you connect all the gates, flip-flop, and storing element with wires, we call that a netlist. Nowadays, we don't design integrated circuit by hand, not by drawing the cells, except if you do very low-level analog circuits. But we use HDL, so hardware description language, and the most well-known are Verilog, which now is becoming System Verilog, and VHDL. They are both languages that have been designed in the late 80s and early 90s. And they try to abstract hardware description as much as possible. So you start by creating blocks, and within blocks, you divide a block in many blocks. And at the end, you try to write the logical equation to describe how the value will be transformed. So usual design flow, if you don't know it, for circuit design is starting from HDL. So you still have to write, let's say, the code of the circuit. Maybe you can still use drawing for assembling a large component. And you can do simulation in order to check the design. And if the simulation is correct, so it's mostly for verification. And if the simulation is correct, you can start to do synthesis. And synthesis is a process by which an HDL description is transformed into a netlist. In addition to simulation, you can also do some formal verification, but usually formal verification use the output of synthesis because it needs to have knowledge of very low knowledge about gates and memorizing elements. So once you have created a generic netlist from synthesis, it becomes mostly a more simple process, because you have to map this generic netlist to a target specific netlist. So it will try to convert cells into the one that exists into in your target, or maybe merge many cells into a more complex cell that exists in your target, or simplify one into multiple cells from your target. And once you have a specific netlist, you can try to place and route it in order to fit into the physical implementation. At each point of this flow, you can have bugs or failure. So for example, if the simulation is not correct, it means that you have a logical bug in your HDL. If maybe synthesis can fail because you are using a non-synthesizable description. Map can fail because you are using a memory that doesn't exist in your target. And place and route can fail because maybe your design is too large, or at the end, maybe because your design is too slow and doesn't achieve your required speed. The two main used kind of integrated circuit for numeric application are ASIC, which in that case you have almost full control of what you can put into your circuit. But it also means that you have to create mask and go to a foundry. So it's quite a very slow process, and also a very expensive one, because masks are very expensive and the process is also quite expensive. Or you can use FPGA, which are, let's say, ASICs that can still be programmed. So as you can see on the left-hand side, it's circuit with already placed cells and wires, but you can program how the wires are connected together, and you can also program the content on the cells to do the computation you want to do. So now you know a little bit more about the usual and the simplified design flow. Let me introduce what are the free and open source tool for that. So if you start from the standard language on the right hand side, so the two main standard language are Verilog and VHDL. And for Verilog, you have Variator, which is a very high speed tool that translate your Verilog or system Verilog input into a C++ set of files that are then compiled and executed. The main drawback of this approach is that Variator only supports a subset of system Verilog. And the other tool is Icarus Verilog, which is a little bit more traditional, and it also interprets the Verilog or system Verilog input. So it is much slower, but I think it still supports a slightly larger system Verilog subset. For the VHDL camp, the two main tools are GHDL, which was almost already described by Anton, and NVC, which is, I would say, a slightly less advanced tool. One of the main advantage of free and open source is that they allow people also to create their own language. like Chizell, VHDL, Clash, MyHDL, which are most of them based on well-known general purpose language like Python or Haskell. This language allow you to write maybe more flexible code and more dense code. But in order to do a real chip at the end, all of them need to convert the code into either Verilog or VHDL code in order to go into the design flow. Some of them also support simulation without translating into Verilog or VHDL. One of the possible output of simulation is either a yes/no exit status. So in case of error, you get a no. But also if you want to inspect or let's say debug what happens into your circuit, you can use a waveform viewer, which is like oscilloscope, numeric oscilloscope. And the main first tools is GTK wave. In the FOSS community, you also find a lot of verification framework. So there are either HDL library like UVM, OSVVM, UVVM, VUnit that helps you to do verification of your design, or CocoTB, which is a fully Python approach. So you write your verification in Python, and CocoTB provides an API to interface with your design written in VHDL or Verilog. I would say that maybe verification framework are something that is widely used from the FOSS community. On the backend side, so everything after synthesis, I would say it's less advanced. Most of the synthesis is nowadays done by Yosys, which is an open source synthesizer. It provides a Verilog front-end. But if you want to do VHDL, you can also use VHDL that just acts as a front-end for Yosys. For mapping the output of synthesis, Yosys can do it using ABC. And for place and route in the FPGA area, you can use NextPNR and VPR. For the ASIC flow, it's much more complex and I would say less advanced. The problem with ASIC is that everything that is advanced is completely closed and well closed by the foundry. So it's difficult to do any open source without signing an NDA, which is a little bit antinomic. Why would you use free and open source ADA? Well, you have to know that every FPGA vendor provides already a proprietary toolchain, and they are very complete. Most of them are free in the meaning that you don't have to pay for them. And for many FPGA flows, they are still required because the way, the content of the program, the bits, what we call bitstream, which are the programming element of the FPGA, is not documented. So we don't know how to generate a bitstream for an FPGA, unless it is reverse engineered. Most of the actual current FPGA use IPs for some advanced feature like PCI Express bus or high-speed link. And these ISPs are often encrypted and not easily usable through open source EDA. And it is also, there's also an existing ecosystem around this proprietary EDA tool. But using open source tools make also sense if you are, if you have a coherent mind, because if you are designing open source hardware, it makes sense to use open source tools. So it's part, let's say, of the, maybe of your ideology. You want to contribute to the free and open source community. The price is also often an advantage. Performance can also be an advantage. In particular, we have seen that Accelerator has been widely used because it is often more performant than the commercial tool. Also, as Anton says about feature, I would say that free and open source EDA tools are the only way nowadays to do integrated, continuous integration because you can deploy them without any restrictions. The support for free and open source is often better than a commercial tool for whatever reason. At least that is what is reported by many people. And finally, they offer a much better flexibility. For example, if you want to adapt your tool, you can only do it if you have the sources. Or if you want to run any tool on Power system or RISC-V system, as far as I know, commercial tools are not available on this platform. Thank you for listening and thank you for your time.
Thank you very much, Anton and Tristan. Really appreciate your discussion today. We are out of time for questions, but it is coffee break. And so what I've done in the chat is I posted a couple of different things for our panelists who may have missed this or anyone else to get the link to the next Zoom webinar at 11 o'clock. I put in the link for that, for the participation link through the ICS website, so you can get there. Also in the chat, I posted all of the links to the various people, so you can see if you'd like to continue conversations and talk to them, you can do that. For myself, for Dan, Andrea, Anton, and Tristan, just click on the links and you'll be there. So thank you very much. It was a great first session. Looking forward to the next talks in the next session. We'll be online if you need anything. Have a great day, and we'll continue this again in the coffee breaks, as well as in the open session. So if you're a speaker, click on the link and we'll let you, that will start up. If you are someone that wants to talk to someone, please click on the link for whoever you want to talk to, and you can join the Zoom and go from there. All right, talk to you guys after this, and we'll see you in the coffee break rooms. Have a great day. Bye-bye.